Sample problem number 5, which is hilariously based on an argument I once had with a colleague about the merits of various vehicles. So, of course, I used to make fun of him. So, some hick in a pickup truck wants to push my poor little lowly Japanese import into the Thames. If my car has a mass of 1,000 kilograms, how much force must the pickup apply to my car before it starts to move? The key thing here is before it starts to move, which means we are in a static state. We're going to assume a concrete road surface, of course. Once it starts to move, now things change. When it starts to move, we now go from a static situation to a kinetic situation. And that's what we're asked to find and discuss what happens to the force of friction in that case. In part C, what is the force of friction now that it is moving? There will be a change, and that is because when it's moving, of course, the car is not willingly going in, so the cars would be sliding along the roadway, which would mean that we'd go from the static situation to the kinetic. And then, of course, what would be the acceleration if the force in A is still applied? So if the pickup truck is still applying the same force it did in part A, what would be the rate of acceleration? This question is going to require both coefficients of friction because we have a situation where we are not sliding and sliding. The not sliding will be associated with the static coefficient of friction. And in this case, since we're assuming dry concrete and rubber, we have a static coefficient of 0.1 and the kinetic coefficient would be 0.8. And again, to interpret this, a static coefficient of 1 would mean that the force of friction would be equivalent to 100% of the normal force. And the kinetic friction would be only 80%. So that actually that is a 20% reduction in the force of friction, which means that it's harder to get things moving in the first place. But once they start moving, i.e. sliding, it's a little bit easier. So there's that initial impulse that you need to do to overcome that stronger static friction, but then it becomes a little bit easier to accelerate. So here's what we have in the given section. We know that the mass of the vehicle that's getting pushed is 1,000 kilograms. The static coefficient of friction is 1, and the kinetic coefficient of friction is 0.8. We are looking for the force that the pickup truck applies, the change that occurs in friction, the force of friction when it's sliding, and that is our force of friction kinetic because it is sliding. And of course, we're looking for the acceleration in that case. So the relevant formulas are going to be as follows. F net equals ma. Force of friction is equal to mu Fn, whether it's mu k or mu s, and Fg equals mg. And the main reason why is because we are talking about the force of gravity and its relationship to the normal force. And I also notice one small little tiny detail here. That should be a capital N. Let's take a look at situation A. So we're looking for the force of the pickup truck in the static condition. In the static condition, that means the acceleration is 0. In this particular case, we're not rolling. So the pickup truck is applying its maximum force against the static force of friction. The important thing to understand is the force of friction static is a reactionary force, which means that force of friction static is always going to try to counterbalance whatever the applied force is. What we're going to calculate is the maximum value that the static friction can possibly produce. So there's a maximum. We'll clarify that as we go along. The important thing to note is that the acceleration equals 0. That means the net force along the x-axis is 0. Why are we specifically worrying about the x-axis is because the force of the pickup truck is along the x-axis. The only two real forces that are acting along the x is the push from the pickup truck and the force of friction. Dropping vector notation, however, we know that F net x has to be 0 because it's not sliding yet. The pickup truck is pushing in the forward direction and the force of friction static is resisting. And looks like I forgot to put my subscript statics on here. So isolating for FP, we bring this negative force of friction static to the left-hand side, making it positive. So now we're just working with magnitudes. Force of friction static is equal to mu Fn, but specifically, since we're talking about the static coefficient of friction, subscript S. And I'm going to call this new equation, equation 1. Fp is equal to mu S Fn, which is equivalent to the push force of the pickup truck. The push force of the pickup truck will be equivalent to the maximum value of the static friction. However, we don't know what Fn is yet. Now you have a pretty good idea that Fn equals Fg, but you can never assume that because there are cases where that is not necessarily true. But we're going to do a little aside here. and we're going to find the normal force. Now we know that the normal force is in the y-axis, so hence we're going to look at F net y. F net y is equal to our Fn plus our Fg. But since it's not floating or sinking, the net force in the y has to equal 0 newtons. No acceleration in the y component, therefore F net y equals 0. Normal force is positive, force of gravity is negative. Bringing the force of gravity term to the other side, we get Fg equals Fn. Turning the equation around, I get Fn is equal to Fg, but we know that Fg is equal to mg, that's equal to the weight. So therefore, Fn is equal to mg, and that's going to be my equation number 2. I sub 2 into 1, and I get the force of the pickup truck is equal to mu s mg. And this is a new equation, equation number 3. Now we can substitute our values in. The static coefficient is 1. The mass of the the mass of the car, I should say, is 1,000 kilograms times 9.8. So the pickup truck is applying a maximum force of 9,800 newtons. This is the absolute limit that the static friction can withhold. So if the pickup truck pushes with no greater than 9,800 newtons, nothing will happen. But if the pickup truck applies just a fraction of a newton greater than this amount, immediately static friction breaks and kinetic friction takes over. And when I'm talking about a marginal amount, I'm talking about 9,800.000000001. Anything past this amount, static friction breaks and we drop down to the kinetic friction, and then the whole system dynamics changes in an instant. So now let's talk about what happens in part B. And this refers to what happens to that change in friction. So again, the big idea is that the static friction will try its best to match the push force. And redrawing this, I realized my static friction vector was a little too short. So if the push force was this much, then the static friction would only push just enough to match. But of course, once we reach this maximum amount, static friction cannot possibly produce any more. So immediately what will happen, so if this vector gets a little bit bigger, our static friction is gone. And then immediately we drop down to our kinetic friction, which is 20% less. So then this turns into the force of friction kinetic once it starts to slide, which now takes us to part C, where now we're trying to find the force of friction kinetic. The acceleration is now no longer 0 meters per second squared. The acceleration is in the positive direction. This implies we have sliding. And now that it's sliding, it's the kinetic friction that applies and no longer the static friction. So our kinetic friction is significantly smaller than our static friction, 20% less. But the pickup truck is still maintaining its original force, which was 9,800 newtons. Now, technically, it had to be 9,800 plus a tiny little bit just for enough to break friction. And once that happens, friction drops, and now we have this imbalance between the two. So the poor Japanese import is going to now accelerate in the forward direction. Calculating the force of friction kinetic, we know that that's equal to mu k times Fn. But we already found Fn in the above question. We already derived an equation, equation 2 up here, where Fn equals mg. Substituting in, we replace Fn with mg, and now we have equation number 4, where the force of friction kinetic is equal to mu k times mg, where the force of friction static was mu s times mg. Putting in our values, we get a force of friction kinetic that is 7,840 newtons, which is much less than the 9,800 newtons that the pickup truck is applying, hence why we have acceleration in the positive direction now. Finally, finding the acceleration. And again, doing things algebraically. And when we do things algebraically, like I mentioned, technically speaking, we have the numbers already. But my goal is to show you how to solve these things algebraically. The main reason why is because once you get to grade 12 and university, there will be entire questions where you cannot solve them without doing them algebraically. This means, in this case, when we take a look, we have F net x is equal to Fp plus the force of friction. Of course, these are in vector form. Dropping the vector notation, we have ma, which is the net force acting on the vehicle, because F net equals ma. The push from the pickup truck is positive. The force of friction is negative because it's working against, and we're talking about the kinetic coefficient of friction. And the argument, I'm aware, is the following thing. You know what this number is. That was 9,800 newtons. We just calculated this. That was the 7,840 newtons. We know what the mass is. We could literally solve this in 2 lines. And again, that is 100% true, but that is not the point of what I'm trying to do here. Again, what I'm trying to do is show you how to get these more complex expressions. So what we're going to do is we're going to substitute in our equation 3 and our equation 4. Our equation 3 was this: Fp is equal to mu s mg. And our equation 4 is force of friction kinetic is equal to mu k mg. So when we make those substitutions, you're going to notice something. Once I did this, every term now has a mass in it. And since every term has a mass, we can divide both sides by m and then eliminate that. And that simplifies it. What's really neat is the realization is that the acceleration doesn't actually matter on the mass of the vehicle. It has everything to do with the relationship between the static coefficient of friction and the kinetic coefficient of friction. So no matter what vehicle I used, we would get the same rate of acceleration if the friction slips. Now we have the following expression. The acceleration is equal to mu s g minus mu kg. I'm going to take a common factor of this little g. So divide little g out by both these terms, and that gives me mu s minus mu k equals g. Now that is a beautifully elegant expression for the acceleration. So the acceleration of the vehicle is actually independent of its mass. Any vehicle that's getting pushed where it finally slips will accelerate at this rate. And it's just the difference in the coefficients of friction multiplied by the acceleration due to gravity. Substituting in, we get 1 minus 0.8 times 9.8, and this gives us an acceleration of 1.96 meters per second squared.